The purpose of this video is to show a few different workflows for the design of transfer beams, either RC or PT, in Adapt Builder. And we're going to use tributary load takedown as well as the global FEM solutions and reactions for this video. In this video, we're going to be using Builder 2019, and we're going to make sure we have Edge with Floor Pro turned on. The transfer beams we'll be designing are at level 6 of the structure, so we want to use Floor Pro for those designs. We're also going to turn on the mode for PTRC in order to model post-tensioning as needed, and we'll be working in US unit system today. Let's go ahead and open the model. And we're going to first switch over here to multi-level mode. We'll go ahead and rotate this in 3D. This has some ramps in it, so we get that message with ramps. You can see the structure actually looks elongated. We'll just make sure under the scaling we reset the scaling to default. So we have the proper aspect ratio for all 3 directions. And then if we go to level 6, we're just here setting our active plane. And I go to single level mode, you can see we have a transfer condition here. So there's a column. We'll go ahead and mark this column. There's a stack of columns here, and they transfer out on this beam. And you can see currently we actually have post-tensioning cables in this beam. It's a harped profile for the design of that beam. So the first workflow we're going to look at is, we're going to call this the direct FEM solution, and it's based on a global model. I'm going to go back to multi-level mode, and we've already meshed the structure. So if we're in multi-level mode and we use the function analysis mesh generation, it's going to mesh the entire model, and that's been done. So I'll go ahead and I'll execute the global analysis for this entire model. One thing to point out here is that we currently are not analyzing the model with any stiffness modifiers. Everything here is set to the uncracked usage case, where we use essentially 1 for each of the modifiers, a multiple factor of 1. We also have a usage case called cracked 50, and this is set to 50% of the stiffness for different components like walls, columns. So the user can set up additional usage cases by double-clicking on any component, going to stiffness modifiers, and you can see in the property table there's uncracked, which is the default. This is locked. You can't modify those, but you could go in and modify, cracked 50. Clearly, we don't want to modify the columns one by one, so we could always select by type, for example, columns. Once I define the usage case, then I can modify the selection of columns that I've selected under this option here. So I could go in and write the modifiers in this way. We could do the same thing for walls, for example. If I select all of my walls by type and I go into the modify selection dialog again, under wall we have the ability here to set the stiffness for walls for that same usage case. You could do the same for slabs, beams, and so on. So we're going to run this just for this example with no modifiers. Everything is set to 1. I'll go back and I'll run this globally. I'm going to run this only for these 2 strength combinations for this example, and we'll use uncracked, and we'll go ahead and run this. Okay, so while this is saving the solution, remember the first workflow we're going to call the direct. This is the direct, and we're going to say this is direct from FEM. So what this means is that we're going to run, we have run the global FEM solution. If I save that and I, for example, go immediately to that transfer level and I look at, for example, the column axial forces under actions, axial force. This axial force, let me go to a wireframe view. It makes it a little easier to see. Here we have a force of 704 kips for this particular combination. So In this case, there's no need to rerun the model in single level mode. We're going to use that direct force that was captured through FEM global run to design the transfer beam. So now if I take this beam and if we go back to floor design, I'm going to turn on the strips for this level. We may not have any strips. Let's go ahead and create a design strip. So I'll use them the X direction, and we're going to go from end to end like so. And then I'm kind of isolating the beam from the rest of the slab here. Typically we would have support lines on all beams if we were to design the entire system, but here we're just isolating one. And I'll go in and I'll add a splitter. So the splitter might look something like this. And then we'll do another splitter here somewhere. So we'll do a splitter from there to there, and then to there. Okay, and that's going to break the beam into its own separate strip. We'll generate the design cuts for that beam. And while we're in this dialog, I'm going to turn the tendons, and I'll show us how to remodel the tendons here. So we'll delete that tendon. So now this becomes its own unique strip. If I double click on that strip, I'm going to set it to beam design, and I have the ability in this version 2019 to consider the effective flange for the design of the beam. So I could select this and set up my criteria for the beam design, and at this point I can just design the sections from floor to. So I can go immediately to design the sections. I'm not required to reanalyze this slab. We already have a solution in place. It's the global direct FEM solution. I'll design the design cuts for this beam strip. And if we go over to the design section options, let me collapse this. For strength dead and live, for example, the bending moment here is around 5,200 kip feet. So the program has actually designed the beam now for this moment. Had I run it for service combinations as well, I would have also included minimum reinforcement for the beam. So if we double click on, for example, this design cut right here, go to design sections, you can see there's a requirement of 33 square inches of steel for the beam. That's a lot of reinforcement for the beam. The beam may not be sized properly to begin with, but you can see it's 18 by 42. So that's how we would design it using a direct FEM method. Now if we say, well, this beam needs post-tensioning, so we're going to add bonded PT maybe to the beam. In this case, let me just turn off the display of the design cuts. I'm going to go now and add PT. So I'll add a cable from here over to there, and maybe this exits out there. So there's my cable, and if I dimension this, the tendon starts here at the top end, so I'm going to dimension from there to the point of the concentrated load, and also over to here. And if we take that ratio, this point load happens around 0.4 times the length of the tendon, or the length of the span. So for this tendon, we're going to go into that tendon. Let me go ahead and delete that markup. We'll go into the tendon and enter the properties of the post-tensioning. Okay, so we'll say we're going to use calculated force method. The first end is actually going to be the fixed end. The other end will be the live end. I'm going to estimate the long-term loss, in this case, 10 KSI. We could also calculate the long-term loss if we have the PT shop module turned on. In terms of the shape of the cable, we're going to use a harped shape here. So we'll go to a harped profile. X2 over L for the harped cable will be 0.4. And then the width of the straight portion of the harp is defined by A over L. We're going to say that's 0.05. And then we're going to say we want this to be located 3 inches off the bottom of that beam. We have an anchor point here. That anchor point may need to be raised to be at the CG of the effective centroid. So if I go back and turn on my properties, for example, if I look at this, I can see that the centroid for this particular section is actually from the top. It is 12 inches. So coming back to my tendon, I'll turn that back off. If I go back into my tendon, let's change that to 12. We can change this straight extension here. I'll also say that's 0.03. And then we have the same thing on the opposite side. Right there, let's see, that's 0.03. Oops, that's the mu coefficient. Let me change that to 0.03 here. Okay, so make sure those are correct. These variables are defined if we go to this little image. X1 is from left end, X3 is from right end, A, X2 is to the center of A for the harp shape. Okay, so we have that now, and then for the end span, I'm just going to use a straight profiled out to the CG of the slab. If we don't want any straight portion here, I could always define that as 0, and it just goes to a point and back down. So this is going to be the cable. We're going to go in and add, define our number of strands. We're going to use 1/2 inch diameter bonded tendon, so I need to change this over here to bonded system. And if we come back to stressing or general, I'll modify the number of strands. So I'll use 25 strands in this beam. And this might be based on just how much you need for a minimum precompression. Maybe we want to precompress the beam, 200, 300 psi for this transfer condition. We might also have run a calculation to determine the number of strands needed to meet the allowable stress. We could post-process that if we use the tendon optimizer in the program, but for start, we have to enter some number of strands for the beam. So because we've entered a new component, which is posttensioning, we actually need to reanalyze the structure. Otherwise, we don't get an updated solution for the hyperstatic actions from the PT. So this will require us to come back. Because we're first illustrating the direct method using global FEM results, we're going to go right back to global analysis. We now have some posttensioning there, and we're going to analyze the structure again. And in this case, I'm going to run it for both service and strength, so we can see that we get updated results also for checking stresses for that strip. So we'll go ahead and rerun the analysis. Okay, so we've reanalyzed the structure with those tendons in place on that level 6. I'll go again directly to level 6, and we're going to design the sections at this level. Again, important distinctions, we did not have to reanalyze the single level. If we go now to the bending actions again for strength, dead and live, for example, we have a little bit different moment in this. The secondary actions from the PT may not be contributing much to the moment, so that will affect the results here somewhat, because this strength combination includes the hyperstatic actions from post-tensioning. If we double click on the section, you can see we went down from 32, 33 square inches down to 16 square inches because of now the presence of mainly of the post-tensioning in the beam. So this may be more manageable from a design standpoint. Understanding there's an offset there between the PT and the rebar. We can also check, for example, deformation. If we go to a service combination, service total, we might want to check the deflection along the beam. So the deflection is L over 276 for this full span, and these are just integrated deflection values over the design cuts. These are not long-term nor crack deflections. We would likely want to run this entire floor for cracking, and that's illustrated in a different tutorial video that we have. So again, we're just defining the different workflows here. Okay, so that's workflow 1. Workflow 2, we're going to actually come back and go to back to the global model. So this will be workflow 2, and this is going to be tributary, I'll call it tributary load takedown. Okay, and this is going to be a method that we'll use, which is completely independent of the need to model or the need to run a model for finite elements. So if I take this model now and I use this option, this model includes loads on all levels, and I use load takedown, I'm going to generate Verneuil-based tributaries for the structure. And so we'll regenerate and recalculate the tributary load takedown based on these tributary regions that the program has produced. And the user could go level by level and dig into some of the results using these load takedown tools in the result browser here. I'll recalculate the loads. Okay, once the loads are calculated, I'll go back to level 6 just to illustrate what's going on here if I actually need to go up one level. And for load takedown, I'll turn on the cumulative loads. And you can see at the bottom of the level or the column above level 6, you can see the loads dumping into level into this column on level 6, below level 6. So there's 233 kips of dead load, live load, and self weight. Now, in this case, the relative stiffness between this wall that's in close proximity to the column has no effect because these loads are purely based on the tributaries that are produced. So you may see some pretty significant differences between a tributary-based approach and a finite element global approach, where in the first run we saw that this load was pretty much smaller than this set of reactions. So we're now going to design this beam again at this level, but we're going to essentially apply this reaction at the beam. In order to apply this tributary reaction, I'll call it TR, at this beam, I have to rerun the analysis. So I'm in single level mode now, and we're going to go up to analysis. This has already been meshed. If I wanted to redo the mesh, I could, or I could illustrate the mesh here graphically using these visibility tools. But this is already meshed. We'll go to analysis. I'm going to rerun the analysis, and now I'm going to include load takedown. And you can see we have a reaction for dead, live, and self-weight based on not only tributary, but also on the previous run for the uncracked solution. So we can run it for tributary, rerun it for the uncracked solution, or for envelope. And we're going to first run it for tributary. So this becomes just a completely different, let's say, snapshot of the model in terms of how it's being analyzed. We're looking at it only in single level mode. There's no structure above or below that may alter the way that the forces are distributed from a global finite element perspective. And so this is assuming, maybe let's assume you have a spreadsheet and you've formulated all the tributary loads, and now I want to just put that load on the beam itself in a single isolated type of a model. This is similar to that type of a condition. So we're now going to rerun this with the load takedown reactions. Okay, and I can go immediately back. One thing to note is if I go into this viewer, we can see for this run, for example, for service total, I might want to look at the vertical deflection deformation, and you can see there's quite a bit of deformation here under this point load produced by tributary. But this may help to see just the behavior of the structure. I can go back into the main model, closing that module for the view analysis results. I'm going to now just again design my strip based on the new solution using single level with load takedown. So we'll design this. Okay, and you can see the moments. So the moments here are much higher than what we saw previously. And that again is mainly due to the finite element result for global. Most of this load vertically was sucked into this stiff wall here. Very little was going to this column. In this case, you have more of a one-to-one relationship in terms of the load going to either component purely based on tributary. So when we run this design, we obviously would get something different in terms of the rebar We may need to add more post-tensioning. It's really up to the user how they want to approach the design using load takedown, which is just a method where we can quickly accumulate the loads based on tributary, or using the finite element approach that we ran previous. The third way to do this is, I'll call it an indirect approach, and it's using the FEM reactions. So rather than using tributary reactions, I'm going to rerun this single level with the global reactions, with the global FEM reactions. And I can go right back to execute the analysis. Instead of using tributary, I'm going to switch this to uncracked. And I'll go ahead and run this now with the finite element reaction that the program has stored from the first run that we made. We can immediately design these strips again. Okay, and we get a moment now of something much, much smaller here, because again, the force in this column is the 700-800 kips that we saw when we first started, but now we're applying it to a different system. We're applying it only to a single level model, which behaves differently than running this design strip relative to the global solution. So not all models exhibit this level of difference in terms of tributary and FEM, but it's really important that the user pay attention to how the model behaves, what the assumptions are for stiffness modifiers, and whether or not they want to use the tributary option, the FEM option, or the envelope of both. The last thing we'll show is if I wanted to run this beam with a modifier, let's assume I wanted to crack the beam and design it as it's cracked, I could always go into this beam again. We'll go over to stiffness modifiers. I'm going to edit and add a new usage case, and I'll call this transfer beam cracked. Okay, and then we can modify those values directly for only this beam in this dialog. So we can modify flexure about 1 axis, flexure about the 3 axis, which is our main bending action here. We may have some torsion depending on the load and the geometry. We'll just modify both. We'll say this is 0.5 and this is 0.5. Okay, we'll save that, and now I can run. Everything else is still set to 1 for that particular usage case. You can see this is still 1. The slab itself set to 1. So the only thing modified is that beam. We can rerun the analysis again, and I can use that transfer beam cracked modifier with whatever reactions I want. So here we're going to use tributary reactions again. And now I get an updated design using the second method, single level with tributary reactions, and the user could evaluate a beam under different scenarios for cracking and also where the reactions stem from. So last step is we'll design this one more time. Okay, we get another value there for moment. If we look at that beam design, you can see there's a lot of still there. This looks like it may not work, but again, we're showing a process involved in using the software. If you have any questions about this process or would like to discuss, please contact support@adaptsoft.com, and we'd be happy to help you out. Thank you.